Presentation, I'll cover a small introduction of the industry, and I'll do the overview of the 2G, 3G, and 4G network, and then cellular IoT network concepts, and the 5G network. Next, I'll do the key technologies for the future network deployments, and finally, the what will be in beyond 5G. Okay, when you see the Sri Lankan economic industry state that we have 74% of the unique subscribers. That means only 26% of people does not have a connection. And network coverage wise, that Sri Lanka has 97% of coverage, which is very good value. And 1.98 SIMs per unique subscriber. So almost 2 SIMs per subscriber. And the connection also continuously increasing. For example, 2012, 18 million, now end of 2020, we have 32 million. So market penetration is 150%, so it's beyond 100%. So ARPU is the average revenue per user. So it's above $4. So this is one of the lowest in the world. So now it's even lowest because the dollar rate removed. So the revenue also, we had better revenue growth until 2020. After that, we had the COVID. So COVID also has a very big impact on mobile networks. For example, here that I have data for UK, USA, Brazil, Mexico, and India. So you can see all the countries has lost in the GDP, the blue color. But US also the loss in the mobile network as well. But if you compare with the India, that even the GDP is declined, the mobile revenue has increased by 17%. So this case is there for Sri Lanka as well. The main reason for that is that US, UK, they have fixed line networks are very prominent and very well established. So therefore, when people start in not moving, so people starting to work from home or like of a stationary working, so they use the fixed line connection. But in Sri Lanka, we don't have fixed line connections. So even the people is not moving and stayed in the home, we had very high growth in the mobile traffic. So because most of the people use the mobile network as their first choice of connecting to internet. So that's why countries like Sri Lanka, India has huge growth in the mobile industry with the COVID-19 pandemic. That is the case, but currently actually the industry is struggling because of the power crisis and all the things. So sometimes we may have to shut down some services in the future. So we'll see what happens. So we'll predict the best, but not sure what side will go in the future. Okay, now I'm moving to 2G, 3G, 4G, and 5G era. As I said previously, that 1980s we had 1G. So each 10 year we have generation. So 1999, 2000, 2010, 2020 is 5G. 2030 we're expecting 6G. So 1G is an analog system. So now we haven't, I think you may have sometimes used, or you may not have even seen an analog device. But 2G definitely you have seen. So 2G is 1990, almost 3 decades ago, all technology, but it's still dominant. So it's a very good one, actually still profitable and still dominant. And 3G came 2000. The 3G is introduced this data, so mobile broadband. So 2G is for voice, and 3G mobile broadband introduced. And 4G, when you come to 4G, so you could able to have very fast high-speed internet and high-speed mobile broadband. So, and when we go to 5G is something like connecting everything. So you have the high-speed internet and IoT applications, as we discuss, and we'll discuss in the later slides as well. So this is how the evaluation went on. And from the 2G, so we have digital system, 1G is analog, and the 3G is the mobile broadband, and 4G we call video. So because we can have much better video quality with the 4G, and the 5G, so we get 4K video, and the connecting everything is for the 5G.
Chami, can you go to previous slide? And these days, in our mobile phone, we can see the 4G. Then suddenly it will go to the E. What is that E?
E is for the eGPRS on 2G.
2G. Yeah.
Yes.
It's another technology.
Yeah, this is 2G. Actually, this is first 2G, and then later the 2G we have GPRS, and later we have eGPRS, because time to time this technology improves. So the latest available internet connectivity for the 2G is eGPRS. So
eGPRS, what is the maximum speed you can go normally?
It's normally, I think,
2 megabit per second?
No. Maybe 192 kilobit per second, if I can remember.
That's why we cannot go to get the internet connections at that time. No,
so you are referring when the power failure, right?
Yeah, power failures.
Yeah.
That is the base stations automatically switch to 2G.
No. The power failure, actually what we are doing is we try to save some energy. So most probably in your area 3G site is shut down with the power failure. That's why you are getting to 4G, because
4G,
maintaining all the 2G. Maybe otherwise you should be served with the 3G. That is the priority. First priority is the 3G. If it is not available, then you to go to 2G.
If it is 4G, automatically going to the 2G, no?
Yes, because I think, sir, that your area will not have 3G when the power cut is there. 3G will...
No, when I move in, I observe in some areas it is HE, some areas 3G like that. That is the reason. If the 3G is not there, it is going to 2G, no? That is
2G,
E.
yes. Yeah.
Okay.
So in the mobile network, that we have an important concept which is the cellular concept, right? So when we compare with the mobile network with the fixed line connection, like SLT fiber or something, that in the fiber connection you have a cable to your home, right? So that cable belongs to you. Whatever the communication you are doing with the network, you can use that cable. That's belong to you. But in the mobile communication, it's different. So the cable is the free space, right? So cable is our environment. So there's only one free space. So everybody use the same interface, right? AI interface. So there's a lot of competition there. So because not only you are using that free AI interface, so there are many other communications also happening in that AI interface. So very difficult we to deal with this AI interface. So one thing that we have do, the first thing in the cellular communication is the cellular concept. So you have heard the cellular forms, right? It comes with this concept that what we are doing, we divide area into cells, right? So we can call one of this area is a cell, right? So, and this is another cell, and this is another cell, right? What we are doing, so we we position our base station or tower in the middle of this kind of a cell, and we put 3 antennas to 3 directions, right? So one base station will provide coverage for 3 cells, right? So then what we are doing, so then we select another location like here, and we set up another base station and create 3 cells, right? So this cell, this tower will, these 3 cells, this tower will provide for this, these 3 cells. Likewise, we can have base stations position. So what is the important thing here is that, so if you cannot, you can use the frequency efficiently. For example, let's say one base station, let's say they assume that you can only have 25 calls simultaneously, right? If you can have 25 calls simultaneously, and if you are in a particular area and everybody can have only 25 calls, right? But if you can divide that particular area to 2 and have 2 base stations, right, and you make sure that this signal doesn't go to the other side, and you can have another 25 calls, right? Likewise, dividing the area, so we can increase the capacity, right? So this is the concept in the cellular network. So this is the basic concept. Even the 1G, 2G, 3G, 4G, 5G, 6G, everything use the same cellular concept. So we have improved this concept in those generations. So we can further increase our capacity.
So we have to control the power, not to interference, no?
Yes.
With the cells, within the cells.
Yes. So different, let's say for the 4G, we use the same frequency. For 2G, we use a different frequencies. Different technologies are used to limit the interference. We'll discuss that later.
Okay, right. Thank you.
Okay. Next, I'm going to discuss this 2G and 3G. So this is now we call the legacy technologies, or quite old technologies. In the 2G, this is the network architecture, network topology. The mobile connect to the base station, so it's called this BTS, the term used in the 2G. And then there's a thing called BSC. It's the base station controller. So base station controller typically have the intelligence on the radio side. And then we have the MSC and the SGSM. So normally we call this segment is the RAN, or radio access network. And the other side is the core network. This is core network. So core network is basically located in a central location of the operator's premises. The radio access network located in, it's distributed all around the country. And the BSC is somewhere is like a regional distributor. For example, for the north, there can be one base station, BSC. For the southern province, another BSC. Likewise, this is a regionally located. The BTS, you know that everywhere we have towers. So this is how this is located. So what is the happening in the BSC, in the GSM, that you can have either voice or a data. So the typical one is the voice. Sometimes you may be using for data. That is that eGPRS or GPRS. So when you are making a voice call, what happens is that your phone connect to the BTS and then to the BSC. As it is a voice call, you will connect to the MSC. MSC is a mobile switching center. So where your call is be connected. So it will ring the other side, and the connection is made using this node called MSC, mobile switching center. And there are some other VLR, HLR, those are supporting devices that for the MSC. And let's say if you are taking the call for, let's say for the other vendor, sorry, other operator, SLT line or Dialog or Hutch or whatever the operators, then this will go to the gateway MSC to that operator's network. Maybe you're the roaming or whatever the network you are in. If you browse the internet, not the voice call, then you will not connect to the MSC, you will connect to the SGSN. SGSN is the data side, right? So SGSN is a data controlling node. So from SGSN, you will get to the GGSN is our gateway router function is there. And from there, you will go to the internet, right? So there's a two difference between these two kind of traffics, because the voice is, we call it circuit switching. So, and the data is packet switching. So, you know, packet switching, I think it's all the IP related, and source IP and the destination IP is marked, and we send on this interface, and it will travel to the internet. But then the circuit switching is something new. It's actually a very old technology. What we are doing is we create a circuit from here to whatever your other base station, let's say here other caller is here. So we create a dedicated circuit from your phone to the particular recipient, right? So here the thing is that you have guaranteed tunnel is created inside the network in the circuit switching. So the packet switching, there's no guaranteed tunnel. So when the link is not congested, so you will have high quality, but if there's a congestion in the line, so sometimes the packet will delay and cause some problems. So there is a difference in circuit switching and packet switching, right? As the circuit switching create a dedicated tunnel, so this is kind of expensive nowadays. While the packet switching, I mean the cost-wise, is cheaper, right? So in the 3G also the same architecture, only the names are changed. So the base station BTS now called Node B, BSC now called RNC, and all MSCs, HGSNs, GGSN, and everything is there, right? So That's the architecture of the GSM and UMTS network. GSM is a 2G, UMTS is for the 3G. When you summarize the GSM network, in the GSM, what we have is that how we are doing this GSM modulation. So we are using 200 kilohertz channel. So compared with the current other new technologies, this is very small channel. For particular user, we assign 200 kilohertz. If you're making a call, you will be given a 200 kilohertz channel on this AI interface. So typically this channel can use only for one person. For example, if you assign this channel, so you can only use that. You cannot share it with any other else. But we use the technology called TDMA in the GSM so that we can share that particular 200 kilohertz channel with others. So this technology is very simple. In the TDMA, what we are doing, we don't give you the channel all the time, right? So we divide channel into 8 time slots, right? First, I am using the channel in 1 time slot and ISP. Then I'll not send in anything. Then someone else will send their message. Then another one sending their message. Likewise, after another 7 people successfully send their message, I get a chance to send my message, right? So this is how happened in the TDMA. So what I'm doing is, so this switching is happening in the millisecond. So this frame is 4.615 milliseconds. So you don't feel that you are being disconnected. But the other thing is that whatever you speak with this duration, you will compress and put it in the 1 time slot. So all the things you talk will be sent to the other side with the compression, and the other 7 users can also use the channel sharing with you. So that's how we shared this wireless technology, wireless resource with many other people. So here we use the hard handover. So hard handover is that when you are taking a call and moving from one base station to other base station. So you have taken the call and you're moving. So your call has to be transferred to the other base station. So normally you don't notice that you are being transferred, but in the 2G, what will happen is we call hard handover, because as soon as we disconnect, we connect to the other tower. So there's something called soft handover where it connects the both for certain time and smoothly handover. So we can see that in the 3G. But in the 2G, we have hard handover, just cut down this connection and create the new one. So this is how the 2G handovers are happening. So 2G is basically not for data, so it's a low data speed. So developed mainly for the voice communication, but still used by many countries as a trusted voice network. So many developing countries, still 2G is dominant. So there are many people, even in Sri Lanka, who don't need the data connectivity, just they need to have voice calls. So it will take some time to 2G to shut down. The next thing I'm talking about, what's happening in the 3G. So this is a 3G one. Yeah, 3G, we are doing spreading and despreading. So 2G, we are using TDMA, time division multiple access, because different time slots assigned to different users. Here in the 3G, we use CDMA, code division multiple access. So we assign the code for different users, right? So we call this typically the WCDMA, wideband code division multiple access. Wideband means we use a wide bandwidth of signal, right? So 2G, it's a 200 kilohertz, but for the channel bandwidth for the particular user. But for the 3G, we use 5 megahertz. It's very large when compared with the 2G, 200 kilohertz to 5 megahertz, right? So this is the bandwidth of the 5 megahertz channel. And in this 5 megahertz channel, we send everybody's signal, everybody's data. So how to differentiate is we use code. So this is spreading sequence. So your information is multiplied with the spreading sequence and then transmit, right? And when you receive, you again multiply with that particular spreading sequence and you will get your data, right? So some other person will send his information with his spreading sequence and also transmit in the same channel. And he has to be spread using his spreading sequence. Likewise, each user's information is encoded or not encoded, is we call it spreading with a spreading code. So this is a mathematical model, so I just not need to go for that level. So this is how the different users using the same 5 megahertz channel. So they all compete for this 5 megahertz channel using this spreading sequence. So this is what happened in the frequency domain. So this is what your signal, right? So when you spread the signal power is lost, but it will be distributed in throughout that frequency band, the 5 megahertz band. And then when you receive that signal, the receiver will get what the transmitter plus the noise. So this is noise. So always there's some noise added when we transmit it. So we always not get the exact the same as we transmitted. So we have the noise plus the signal, right? So then what despreading is done, but this signal will regenerate and the noise will be removed, or noise power will be distributed. So finally we can filter out what we already initially said. So this is how the 3G principle works. This is called CDMA, code division multiple access. So as summary, 3G network use 5 megahertz bandwidth. Technology is a WCDMA. WCDMA is used as a multiple access method. So code division multiple access. Hard handover and soft handover both use. So even the hard handover is there and soft handover is the most prominent one here. So this has a high data speed compared to 2G. So initially 3G first release in 2000, the data rate was like 384 kilobit per second. But currently, so with the time, so there are different versions or different releases of the 3G specifications currently. So for one 5 megahertz channel, we can go up to maximum 21 Mbps. So this is for 5 megahertz channel. HSPA plus. So you in the phone, you can see H plus. Further, so there's another feature that dual carrier HSPA plus, that the phone can connect to two 5 megahertz channels, that two 5 megahertz bandwidth channels same time. We call it dual carrier. So in that sense that we can double this data speed. So theoretically maximum still can use the 3G's 42 Mbps. So we cannot go beyond that. That's the maximum speed that you can get from 3G. Yeah. Next, when you see the spectrum allocation in Sri Lanka, so you can see this from the TRC website in Sri Lanka. You can see how the spectrum is allocated for each operator, right? So, for example, this is 900 megahertz band. Yes, this is 900 megahertz. Is the band. So we call this is 900 megahertz. This is 1800 megahertz, right? So 900 and 1800. So here that you can see each operator will given some set of frequencies. For example, here the Mobitel has 7.5 megahertz channel in 900 band, and here in the 1800 band, so they have like 15, 20, 27.5. Right? So operator can decide which bands, which channels that they want to use for the 2G, 3G, and 4G. For example, if the Mobitel can use one 5 megahertz and another 5 megahertz here for 3G, right? So then the users can have dual carrier HSPA plus, right? If there were time that we have like more 3G user, at that time we had like 3 carriers, but user can connect only 2 of them, but the people has more requirement for the data. So we, in the last few years, we had 3 3G carriers. So any two of them users can connect. But now that 3G use is lower, so now we have basically shut down that carrier and it convert it to 4G. So that's how the spectrum is allocated. So this is 2100 megahertz. So basically we have 3 frequency ranges used in Sri Lanka: 900, 1800, and 2100. Typically 900 and 1800 used for the 2G and 4G. So this is 2G and 4G. And 2100 for the 3G. But nowadays, because 2G and 3G utilization is low, sometimes you have 4G in all those bands, right? So let's assume you use 4G in this band. Actually, bandwidth is 7.5. So the 4G is very slow in this band, right? But if you use in 4G in this bandwidth, so you can have very high speed 4G because very wide channel is there. So we'll discuss that in the 4G. Yeah, in the 4G technology. This is the 4G requirement. So 4G initially target 100 Mbps downlink and 50 Mbps uplink. So this is the initial 2010 specification speeds, right? But as I told you, so now we have, even in Sri Lanka, we can go up to 300 something in some places. So now this technology has even increased enhanced the speeds. So the bandwidth wise, so if you can remember that 2G we use 200 kilohertz, 3G we use 5 megahertz, and 4G actually we don't have such one thing. So we have many options. Maximum is 20 megahertz, right? If the operator has 120 megahertz channel, so he can deploy in the 20 megahertz. Otherwise, he can have 15, 10, 5, 3, 1.4, even below the 3G bandwidths, 4G can deploy, right? So even if you see the spectrum, none of the operators, I think, have 20 megahertz, right? So to deploy the 20, so that 20 has to be intact as a one channel, right? So even the Mobitel has 15, Dialog has 15 here and 10 here. So there's a middle, another 5 megahertz Mobitel. So none of them has 20. So 20 is something not possible in Sri Lanka, right? So maybe 15, 10, those deployment are there. There are other things that multimedia broadcast services, the throughput is higher, simplicity architecture. Yeah, the one notable thing in the 4G is that you cannot have voice. I mean, voice is a legendary application. So the system developed in with the voice of 1G, 2G, 3G, all there was a voice, but 4G, that feature is removed. So that means circuit switching voice is not there. As I said, there's no particular tunnel that guaranteed voice services, right? When I discuss about the 2G and 3G, I told you there's something called circuit switching, that when we make a call, that we create a guaranteed tunnel from your phone to the other recipient phone.
So do you have QoS in 4G?
Yes.
Okay.
Quality of services is there, right?
Then you can give the priority to voice channel.
Yes. Now what we are doing? So now what we are doing, we use the same IP network for voice. So we call this that VoLTE, voice over LTE. So here, then your call is going through the same IP network, similar to what we are taking a call from WhatsApp or Viber. But as we have the quality of services, that means we can guarantee that quality of that voice over LTE service voice call. So that IP path will get highest priority. So then there won't be much issue. Basically, actually, this voice quality is much higher than the circuit switching nowadays. But here you need a certain application in the phone as well. So not every phone is about VoLTE. Some phones, only some phones can go use the VoLTE. The recent phones can use some. If you're using a very old phone, most probably you don't see the VoLTE. So then if you make a call in the 4G, what happens? You will fall back to either 3G or 2G. So when you make a call, you will notice that you connect to 3G network or 4G network to make a call. After you complete the call, you will be redirected back to the 4G network. That happens when you don't have VoLTE in your phone. If you have VoLTE, you can get a voice over LTE over your phone. Yeah, so how this Lte multiplexing is done. So how the multiple people access Lte spectrum. So let's assume for now that we have 20 megahertz for 4G, right? Lte is the same as the 4G. So in the 3G, we use code division multiple access. So each user will assign a different code, and all the information is sent to one large channel of 5 megahertz. The 2G, we use the TDM. So time division multiplexing, each person will get a different time slots. In the 4G, so what we are using is FDM, or frequency division modulation multiplexing. So here, that each user will get different frequencies, right? So we know that total 20 megahertz is for the 4G channel, right? And what we are doing, we create sub channels, lot of small channel uh, within that 20 megahertz band. And what we are doing, we assign certain channel for one particular user. So if you want to browse internet, so we'll assign certain available channels. So you can use these 4 channels, and then you can do your communication there, right? This is quite inefficient because we have to put some guard band. We call it guard band because there are interchannel interference. So this channel can interfere the other channel, so there are problems. So then we have to keep some guard band in between each channel, and this is quite inefficient. So there are a lot of unused spectrum is there, right? So we have developed this FDM in the 4G. We have now called OFDM. So we have put O in front of the FDM. So what is this? It's called orthogonal frequency division multiplexing. So difference here, now we each frequency channels overlap, right? So what happened to the interference, right? Here we even had some space to interchannel interference, but what now we are overlapping the channels. So the theory here is these frequencies are orthogonal, right? So this frequency doesn't have impact on the other frequency. Here that is also mathematically we can prove, but let's say assume that like something like in the vector. So there, if this is 2 vectors are orthogonal, this vector has nothing to do with the other orthogonal part, right? Something similar to here is there, right? So that's why this frequency and this frequency is orthogonal. So there's nothing to do with the other one. So there's no interchannel interference. So using this overlapping technology, so we can use a lot of bandwidth and we can have a lot of subcarriers within that large bandwidth. So that's is the principle of OFDM. So now you will be using 4G, so you will be using few of these subcarriers to connect your phone to particular network. Yes, so this is the same thing. Yeah, other technology that we're using in the 4G is the carrier aggregation, right? So we call it Lte advanced. So Lte is a long-term evaluation. There's a technical term for 4G, and Lte advanced. So sometimes you may see that in your phone it's displayed as 4G plus. In the 4G plus, what we are doing, we aggregate more than one carrier. So here I told you that 20 megahertz is something difficult to achieve, right? Even in the Sri Lankan spectrum allocation, none of the operators can have 20 megahertz. But what can say that they can have many other 5 megahertz, 10 megahertz, they have many of them. So here what they can do, they can aggregate those and provide services, right? So if we here, if you like, let's say in this 18 band, if the Mobiter deployed 10, 15 megahertz here and 5 megahertz here, and let's say another 5 here, right? There are four carriers that altogether 15, 20, 25. 25 megahertz is there that can be allocated per user using this carrier aggregation, right? So that increase the throughput of the user. So maximum 5 carriers can be aggregated, so that 20, if the maximum carrier is 20, then maximum we can go up to 100 megahertz per particular user in 4G using the carrier aggregation. So this is a later development of the 4G. Initial 4G deployment, we didn't have it. We were not having this feature. Now we have 4G plus. Okay. Yeah. My next topic is cellular IoT networks. I thought that will be interested to you guys because of you are working on this field. In the cellular IoT, what we are doing, this is just one example. This is how the sensors are used, IoT sensors are used in agriculture field. So yeah, here they use the sensors to monitor temperature, humidity, acidity level of the water, and soil content, and those things can be monitored remotely using the sensors. So this is similar to the wireless sensor network, but in the mobile domain. So for that, we have this NB-IoT network, narrowband IoT network. So this is one application, but there are many applications for the NB-IoT. So basically, at the China is the dominant player of this IoT. So they has to be in 63% of the global IoT connections in basically in the China in 2023. So China has many applications in the IoT. So if you want to connect one of your applications to the IoT, there are many options. Like, so either you can go with the unlicensed spectrum. So that means so you can have your own network. For that, you can use LoRa, Sigfox kind of networks. These are IoT related unlicensed networks. Or you can use the Zigbee, Bluetooth, Wi-Fi. These are well-known general networks. So you can connect using those options are there. Other than that, we can use a licensed spectrum. So licensed spectrum is this. This spectrum is given to the operator by license, so that none of other people cannot use. So the service spectrum utilization is guaranteed. So it's illegal anybody to use that spectrum is their frequency for their communication. Unlicensed, anyone can use that. Anyone can have their own Wi-Fi, their Bluetooth, but no one can have the GSM in the Mobitel's or Dialog's frequency range, right? So here you can use the existing network for the IoT as well. So 2G, 3G or 4G, or you can use a dedicated IoT network. So what is the difference here is these networks are not built for IoT. These are for the human communication. But this IoT, cellular IoT networks are built for the IoT. So the cost and the features that suits much better for the IoT application. So there are many. So basically in Sri Lanka, we can see Lte, CAT-M and NB IoT. So when you say why cellular IoT, is because cellular has a global ecosystem. So even in the Sri Lanka, we have that network ecosystem, cellular network. So if you with your own network for IoT, that you have to build that all the ecosystems, the base stations, towers, and everything. But when you go to the cellular IoT, that infrastructure is already there, and its reliability, quality service, and the flexibility and scalability, everything is there within the cellular IoT network. So that's why cellular IoT is more common when you consider to deploy your application, IoT application, when you decide to deploy IoT application wirelessly. So this is a comparison of the network capabilities. Let's say we will compare with this one. This is release 8 CAT for 4G devices, normally a 4G phone, right? So normally a 4G phone will support 150 Mbps downlink for 4G. And
what is this
Mbps.
release 8, release 13?
Yeah, this is a 3GPP release, because this specification is released by the organization called 3GPP, right?
3G partner project, no?
3GPP, yeah, 3G partner project. So they will
cellular standards are defining from there, no? Mobile standards are.
Yes.
Is that correct?
The original way is the standard requirement and everything comes from ITU, International Telecommunication Union. They said this 4G network should look like this. And other organizations come suggest, and this is my 4G and this is my 4G. So 3GPP, one of the organizations feeding for the ITU. There are like IEEE, they also have 4G specifications, but they are not widely adopted. So adopted one is the 3GPP.
3GPP was formed because actually the first 1G was only for particular country only. Then the 2G went to region wise. When it's come to 3G, people want to go to the global standard. Since there are different standards, they get together and have a forum called the 3G partner project. No? So then the global standards are defining from there. Maybe not standard, but the concepts or something like that. So they have the 3GPP release 1, release 2, release 3, release 99 also. They are release 2000 or 00. After that, they came to one digit, no? Release 7, 8, 9,
Yeah,
10 like
now
that.
release 17, release 18, these days are there.
Now the
This
latest one is release 17.
17. Yeah.
Okay.
So
Right.
this is release 8. It's a early stage of 4G. This device can support 150 Mbps. And when we compare that with the NB-IoT that came in release 13, maximum downlink rate is 170 kilobit per second and uplink is 250 kilobits, a very low speed, right? And this is half duplex, so you cannot send and receive data at the same time. And the bandwidth also very small, right? So the 4G normally we call 18 megahertz maximum. This is the utilized one. I told you it's a 20 megahertz, but even the channel is 20 megahertz. The utilized one is 18. So 2 megahertz is in waste, right? But here that what the channel is 200 kilohertz. From 200, we utilize 180 kilohertz for NB-IoT. This the channel is very small, so this channel is the same size as the 2G voice 2G channel. And the complexity wise, if your device is, let's say your normal mobile is complexity is 100%, the NB-IoT device complexity is 15%. So what does that mean is that when you buy the device, or the cost of the device is completely very cheap. If this is a 10,000 rupees cost, this may be 1,500. So the device cost is very less because this complexity is now very low in this NB-IoT. So that because of this, we need the cheap devices. So these are the design target for NB-IoT. So NB-IoT, the one target is to have much more coverage. So our IoT applications are in, sometimes in the basement, sometimes in very far away places, very tricky locations, but you may not have the 4G signals in those places. But this NB-IoT should have coverage even in the basements kind of situations, right? So that's higher, this coverage extension is very much required for the NB-IoT. Further, that battery life. So in the battery life, what here, so we deploy these wireless sensors in the remote locations because we cannot have cables, right? So we cannot have power cables also. So what we can do is we can have set up a battery, and that has to very long time. So in the latest NB-IoT releases, the maximum battery life that they're expecting is 10 years. So that means once you charge the battery you will never need to charge that battery again as long as that device exists. Normally, we don't use a device for 10 years. No? So there is an expected lifetime of the battery life for NB-IoT in the latest releases. But that depend on the application. For example, if you continuously send in messages and receiving data, so the battery will drain quickly. But if you are very rarely send messages, then you can have very long battery life. The device complexity is now very less, that already discussed. The system bandwidth is very less, and the system capacity. The other thing is the capacity. So in the normal 2G, 3G, 4G network, there is a capacity. So we cannot have beyond certain number of users. For example, if they are, let's say, in some panic situations happen, when everybody start to make calls, right? Then the network congested because the network cannot afford that amount of simultaneous connections at one time. So this NB-IoT is made so that we can have like 1 million connections within a square kilometer. So it's a very huge number of system capacity. So this is one of the features that required for NB-IoT. So deployment wise also, now in Sri Lanka also we have both the Lte, Cat-M and NB-IoT networks. So globally, currently there are 170 commercial launches in global. Yeah, my next topic is 5G network requirement or even application. So this I'll discuss about the 5G. Yeah, we talk about this revolution that 90s that we had 2G, 2000 3G, 3G for voice and mobile broadband. In the 2010 and beyond, we had 4G for video, and in the 5G that we will have enhanced mobile broadband. So with enhanced capacity, so this video is more enhanced with support of 4K and 8K videos. Now currently you cannot watch 4K 8K videos because that speed is not enough, right? So other things, the augmented reality. So augmented reality applications need high bandwidth, so you augment the space. And the virtual reality also we have a higher view and basically 3D images being transmitted. So those applications need high bandwidth. So that is supported by 5G. And beyond that, these are something that we can feel that 5G would have, right? Beyond that, we will have a new business opportunities or new applications with this 5G's capability of M2M communication. So that is machine-to-machine communication or IoT kind of communication. So we'll discuss that in the next slide. Yeah. So this is what the 5G technology requirement. So these figures are published by ITU, International Telecommunication Union. So they have in 2012 or something, so they have released this, that 5G network should look like this, right? So 5G network should have the data rate from 1 gigabit per second to 20 gigabit per second. So high mobility, that means even you have that service when you're traveling at 500 kilometer per hour speed, so the massive capacity, so capacity has to be higher. Yeah, so that is what you know, right? There are other two pillars. The what is difference from 4G to 5G here is, let's say that 3G we had 5 megahertz channel, and the 4G we had maximum 20 megahertz channel, the 4 times higher the channel bandwidth. So that means if you take that the wider bandwidth, that means like the wider road, right? So but the difference here, even we wider the road, so all the vehicles are going in the same road, right? So let's assume in three-wheelers, buses, likewise, all the vehicles are going, but different vehicles has different requirements. For example, three-wheel travel very low speed, the car travels very high speed, right? What happens when the three-wheel make the car, then car has to slow down, and there are problems. Like here, 5G we have done separate lanes for separate application, right? So now like we have separate three-wheel lane. Likewise, here we have separate lanes for separate applications. So mobile broadband is a different lane, and the massive machine type communication and ultra reliable low latency communication, there are other two paths are there, right? So massive machine type communication is exact same as NB-IoT. So in the 5G also, NB-IoT is the one that comes under massive machine type communication. So they are the same requirement: high density of devices, high battery life, deep coverage, low data rate. So this is the NB-IoT requirement. So this is different from the what we are seeing from the enhanced mobile broadband. Even you have this feature, you will have separate deployment to have massive machine type communication. And then the other thing is the ultra reliable low latency communication. This is completely new, right? So here it is completely different from these two, right? So in the ultra reliable low latency communication is two key factors is ultra low latency. So that means 1 millisecond latency end to end. So we expect, right? So here we don't expect that much of latency in the normal broadband, but in the ultra reliable we need 1 millisecond latency. And the other thing is ultra reliable and availability, right? So let's assume that the normal massive machine type communication that we set up a electricity bill reader for your home. So each month your electricity bill sent to the CEB, right? But they are delaying that message for 1 hour is not a problem, right? But this mechanism, 1 millisecond, beyond 1 millisecond latency can cause a trouble. So that reliability. So this network exactly should work as we expect. And the availability, there cannot be any downtime. So these has to be guaranteed. And the data rate in moderate level. So this doesn't need like 1 gigabit per second is speed or low as few kilobit per second. So this is moderate, less than 10 Mbps speed. So there are this one is basically used for the applications in this category, right? Ultra reliable low latency communication. One is the autonomous driving. In the autonomous driving, that the vehicles has to communicate with other nearby vehicles and the roadside infrastructure like traffic light and all the roadside infrastructure has to be also connected with the car. So here that the latency is very critical. If the message delays of few milliseconds, there can be a collision. So therefore, the ultra reliable low latency communication is very much required for these autonomous driving scenarios. The other thing is that industry automation. So industry automation, if you have heard the term industry 4.0, so the people call it as the next generation of industrial revolution. So here in the industry 4.0, what we are doing, so we are connecting total industry line into one single communication channel. So here, so everything connect to each other. So when the production line goes on, if some problem happens in some place, entire production is stopped. So therefore, each equipment precisely communicate to each other so that they collectively yield high productivity. So that kind of applications also we need this ultra reliable low latency communication application network. The other most popular one is the telesurgery. In the telesurgery, what we are doing, so let's say the doctor is in Colombo and the patient in Amparo or some remote places, that doctor can do the surgery from Colombo. So he is connected to this kind of equipment, so he can see the patients in that virtual reality kind of experience, and he can instruct a robot with the patient to do the surgery. The robot will get the same instruction of the doctor will do the surgery from the Colombo, but the whatever he's doing will be transferred immediately to the robot with the patient. So robot will do the surgery, doctor will give the guidelines. So there has to be no error. So the message has to be transferred very quickly to the other side. So that's why the low latency and ultra reliable networks are required for this kind of applications. These three, as we already know, this is smart home, logistic management, and smart agriculture. Those we can manage with the massive machine type communication or IoT, NB-IoT. Being coming with 5G. So, but we cannot expect all comes at first stage. Basically, the people required internet at the moment. So this, as I said earlier, that our data traffic almost double in each 1.5 2 years, right? So the 4G will not able to facilitate those requirement, those growth. So definitely we need to have more capacity, so that we need 5G. So when we think about the capacity wise, we definitely has to go first with mobile broadband, enhanced mobile broadband options. But later we will be having the other functions as well. Yeah, now we have to see the spectrum for 5G. The below 2 gigahertz is the frequencies currently we are using for mobile communication. So I said 900 megahertz and 1800 megahertz and 2100 megahertz. These are around 2 gigahertz and below 2 gigahertz. So we call it low frequencies. This is the one currently being used, right? So we cannot see even the 4G, we couldn't find the 20 megahertz channel in these frequencies, right? So for the 5G, we definitely cannot find the high bandwidth required, because 5G's requirement is 1 gigabit per second data rate. So for the 1 gigabit per second, at least we need 100 megahertz channel. The minimum to 100 megahertz, maximum 1 gigahertz channel bandwidth should be there. So we cannot find that channel in our current frequency allocation, current spectrum range. So what we can do, we have to find new frequency range. So there are two options. One is go to between 2 to 6 gigahertz, right? This is something we have been using for other communication. For example, Wi-Fi, we are using 5 gigahertz and 2.4 gigahertz. So we can get 100 megahertz channel from this frequency range, but 100 megahertz will only give you like 1 gigahertz or 1.5 gigahertz speed, right? So the requirement is 20 megabit per second, 20 gigabit per second data rates, right? Still, this will only give let's say maximum 1.5 gigabit per second if you use this frequency band, right? If you need 20 gigabit per second, so you have to go even higher data rates. That means above 6 gigahertz frequencies, right? So this is the spectrum, but problem here that if you use very high frequencies, that these above 6 gigahertz, we call them millimeter waves, because this wavelength in millimeters. This frequency problem is the atmospheric absorption is very high, so it cannot penetrate people, trees, buildings, so it doesn't go too much distance, right? And therefore you need many base stations to cover certain locations. So this is very costly and not much practical. So most practical option is using this frequency and limit your data rate to 1.5 gigabit per second kind of speed. So this is the one actually deploying at the moment. So basically what we are using is 3.5 gigahertz kind of speed band and 100 megahertz channel. So data rate is somewhere around 1 gigabit per second, 1.2, 1.5. Those can be observed in this one 3.5 gigahertz channel. So this above 6 gigahertz mainly used in hotspot scenarios, for example, for shopping mall, for a stadium. So we can have this kind of deployment. So because there are many number of people gathering, and we can have antennas right top on the ceiling, and that was indoor kind of solutions we can go. But the macro base stations or the tower kind of solution, we cannot go this above 6 gigahertz frequencies. So the 5G finally will look like that. So basically the one is deploying on 3.5 gigahertz, and the bandwidth that you can speed that you can get it maximum maybe 1.5 gigabit per second. So even though that we are deploying in the one channel, there are a lot of frequencies that specification. This is 3GPP release 15, so they have given. So for example, the current that we are working on N78, that is 3.3 gigahertz to 3.8 gigahertz. And there are other frequencies like very high frequencies also there already in a specification, like 37 gigahertz, 28 gigahertz. These are also there. So when you buy in a device, that you can see what your device support. For example, this iPhone 12 that support 5G. This band 78 is there. This is what we using, and also this support millimeter waves as well. So that means the very high frequencies also supported by the iPhones. So even in the worldwide deployment, we can see only the N78 has the highest number of deployment. Others have very low number of deployment. So basically N78 or the 3.5 gigahertz band will be the most dominant in the 5G early deployments. This is the effect that I discussed, that when the frequency is very higher, that the coverage is lower. So there's a comparison from 850 megahertz to 76 gigahertz. So 850 is something we use currently for the 2G and 4G, and this is the what we propose for the 5G. So when you see this signal power in the decibel, we can see 40 decibel loss compared to 850. That means signal power is 10,000 times lower than the 900 band. So if it is 2G cell is coverage is something, and the 5G very high frequency will be coverage is 10,000 times lower. That kind of effect is there when you are using very high frequencies.
So that means that when the frequency is increasing, the loss is very high, no? So the penetration of the signal is very less distance, something like that. No?
Yes, penetration is also difficult to penetrate, but sometimes the buildings and trees and the absorption is higher, the penetration is low. That's what happened.
Penetration is low, the distance it can travel is less, no? Compared to the, because of these problems.
Yes, the coverage is less end of the day. So there's one solution that what we can do for that is that normally the antennas transmit signal is omnidirectional, that signal goes everywhere, right? Let's say you have the user here, but to transmit the signal all direction, right? But if you can narrow the beam and project your signal just towards the user's location, so there won't be any signal because there's no any users, right? Then you can use the same power but increase the coverage, right? So you can have much more distance. So this is one method that we are using to overcome this problem. So we are making what is called a beam, right? So this is called beam forming. For that, actually requirements of create a beam, you should have many antennas. So one antenna, if you have one antenna, actually signal is like this, right? So combining many antennas, you can have this directed kind of signal. So that is the thing. So when the base stations has more antennas, so we can have this kind of directed beam for 5G users. So the beamforming is one thing that we can increase the coverage. The other thing is the massive MIMO. So massive MIMO use the beamforming. So not just one beam. So when you have many antennas, you can have many beams for each separate users, right? So this increase the network throughput because each separate user will have separate signal stream. So that means that you can have many signal streams, like many cells, right? So normally we have 3 cells now. So but now we have different users have same streams, so different cells. So if we have 10 beams, that means we can increase the cell capacity 10 times. Likewise, we can have more data and more coverage using this massive MIMO technology. So this is the technology we use in the 5G to increase coverage as well as increase capacity. In the early 5G deployment, actually the 5G was initially planned as a separate standalone network as 4G. So 4G is standalone network, that 4G doesn't need 3G or 2G to run, right? 3G doesn't need any other to run. So they are completely independent network. But 5G also deployed as that, designed as that, but later found out that it will take so much time if we deploy 5G as a complete independent network, because 5G requires more investment, because 5G is using new frequency band. So new frequency band means that the operator has to have new radios and new antennas in their base station. So the investment is high. So this will slow down the 5G deployment. So what 3GPP did was 3GPP introduced 5G version called non-standard. This is the one earliest release we call NSA 5G. So this is a non-standalone 5G. Here it cannot work as standalone. It only need 5G base station in the site, but the core network, the core network doesn't need any change. That 4G core network can use for 5G as well, right? So as this is 4G core networks are connecting, and you cannot just connect to 5G only, right? So for that, the device has to be connect both 5G and the 4G at same time. So your signaling messages, that means the control message of the process messages will be go to the 4G, right? It is the network's maintenance message. You can think like that. So the user to maintain the network sends certain messages to device. These messages will use 4G network, correct? So, but you need high speed internet. For that, you need 5G spectrum and 5G specification. So when your user messages, your data will be go to 5G network, right? The controlling message will go to 4G network, and users data will go to 5G network. So that's how dual connectivity works in the 5G. So this is the initial strategy to deploy 5G in the lower cost, in the very fast, very quick deployment. Otherwise, if you are going with the core networks and everything together, so there's a very huge investment required, and it will take long time to worldwide deployment. So with this one solution, so even Sri Lanka can have some sort of a deployment. So that's what the 5G dual connectivity and 5G NSAs mean. So later, when you can have migrate to 5G core, so 5G core we call NGC. So this is EPC means 4G core. So later we can have 5G core. When we have 5G core, the G node B or 5G base station can directly connect to the 5G core, and we don't need 4G to run in the later stage. But currently, as we do not have the 5G core network, so we use the 4G core network, and we only have the 5G base station to have the 5G services. Other T technologies, yeah. Yeah, there are few other key technologies that I want to highlight. The one thing is that Nfv and Sda. So Nfv is the network function virtualization, right? In the previous 2G, 3G, 4G deployment, what we had, so we had a dedicated hardware, or let's say for the core network. So we have dedicated hardware for particular core network. So the software and hardware comes together, right? But nowadays, what we can have is we can have install that in the cloud. For example, so you have the cloud platform or whatever, the server and the cloud, and then you can have this middleware, the cloud software, and then top of that you can have your core network functions to be run, right? So that is the network function virtualization. So there are a lot of I mean, cost reductions and resource management kind of, there are a lot of advantage for the operator when they go with the network function virtualization, right?
When you go to different versions, you don't have to change the hardware. That kind of advantages are there, no?
Yes, yeah. So hardware life cycle and software life cycle, so we can manage differently. Another thing, and let's say if you are deploying new service, let's say you're deploying the 5G or 6G, that you don't need to take the entire hardware and those things. You just need to install the software. So the deployment time for the new technologies is much faster when you have NFV.
Now, for instance, the example is when you have a router, Cisco router, then you are going to new iOS. Sometimes you have to change the whole hardware, so you cannot upgrade that. In this scenario, that software is separately in the cloud, no? So the whole changes can be done. Only the basic hardware we are using for the connectivity. Is that correct?
Yes, exactly. The other feature in the 5G that we are using is SDN, software defined network. Sometimes you may have heard this. Here also, the typical networking scenario like routers and switches, we remove those routing algorithms, and we have SDN controller. That's the routing is now centralized. So in the SDN controller, you can manage the traffic the way you want. So it is the more efficient way of managing the network. So those two things are coming together with the 5G. Network function virtualization and the SDN. The other thing is the network slicing. That is a new thing that comes with the 5G, right?
Now this
So
Nfv and Sda coming as a service, or it is inside the 5G?
no, it is as a service that we can, NFV is already there, because they are nowadays we don't have dedicated hardware kind of deployment. SDN is something optional there. Either you can go with SDN or you can go with the all routing mechanisms. But SDN comes with inbuilt. So whatever the solution you are buying, so NFV is there. So SDN is something optional.
Oh.
This network slicing in the 5G is what that let's say that you're a company and you need to have your company network in the 5G, right? So normally you company maintain network, no? So now you can have your own company network in the 5G. Here what we are using, we use the same 5G base stations or 5G whatever the hardware available with the network, but your traffic will be routed to different core network, because now we are using the virtualizing technology, so we can have many instances of core network in our cloud, right? So your data, your office data will go to your own cloud, your own core network, and you can have your own regulations on firewalls and everything described within that slice. Likewise, different services can have different network slices. So for example, here the example is that normal mobile broadband is one slicing, and the IoT is another slice. And not just that, so you can have your private network as a slice. So this is a one new application in the 5G. So sometimes you will have your own 5G network within operators equipment with this network slicing.
What is NR? 5G NR?
NR is that term that we use for the 5G. For example, that 4G we call Lte, long-term evaluation. That the 5G is the one, the term is NR, is the new radio. That is the term used for 5G, the technical term.
Okay.
Yeah, the other thing that I thought that will be important to use is this Open RAN. So Open RAN is an alliance that founded by the many telecom operators as well as telecom vendors. So what is they're trying to do, that now you know that core network now we have already virtualized, right? But the radio network, that the base stations and those things, these are very proprietary hardware. So let's say if you buy a base station from Huawei, right? So that all the radio related components we have to buy from Huawei, because these interfaces and everything proprietary, right? So another thing, let's say now particularly, let's say Colombo area, so we have deployed the solution using Huawei hardware, right? So what is happening, so if you need another base station in Colombo area, you have to go with the Huawei. You cannot go with some other vendors like Nokia, Ericsson, or other vendors, because there has to be internet working and all this. There are uh, uh, differences within different vendors, and there can be problems when we have different vendor network in same area. So therefore, so that this radio field is basically vendor dominant. And even let's say for a new particular vendor, new startup or something, they cannot enter, because these companies are very multi-billion company, and you cannot compete with them, right? So these Huawei kind of companies, so they say they have the most of the 5G patents. Also they say that they 1 year ahead of the rest of the world. So whatever the technology available with Huawei today will available in the other companies 1 year after. So that's how they position themselves. So it's very difficult you to compete this kind of companies. But these other companies get together and develop this alliance, that they try to open these interfaces, that these proprietary interfaces now be open, like open source. Now the radio access network is open. So that allowing many startups or many companies to do work on this field, and also the cost is reduced. for the operators, cost will be also reduced. So this is the architecture of the legacy RAN, or whatever the currently available radio access network inside the tower. So what you have, the antenna at the top, and with the antenna you have here in the antenna, close to the antenna, you have the radio equipment. So in this radio unit, generate the radio signals and receive the radio signals through antenna, right? From radio unit onwards, there won't be any wireless communication, all this wired communication, right? So down at the base station, you will have the baseband unit, right? And then it will connect to the baseband unit, connect to the core network, which is we already discussed. What we are doing here, so in the open RAN, so normally those all interfaces are proprietary. So anyone else cannot come up and do their product, because all the interfaces, if this Huawei, it's a Huawei proprietary. It's Ericsson proprietary. So in the open RAN, so open RAN replace this legacy proprietary interface with open standard, so enabling multiple vendors. So what we can do here, so we can have deployment like vendor 1, vendor 2, like this. So different vendors can be within same network. For example, we can further centralize this baseband unit to central location, right, in the cloud, and then connect to different radio units in the base stations. Here also different vendors can be used. So that is the change that comes with the open RAN. So the difference is that legacy historical RAN is vendor dominant. Now it's an open ecosystem with the open RAN. The history older one is inefficient. This is more efficient and more flexible. So the thing here is that even a startup company can work on some of their parts. So you don't need to do everything. So you can find some small application and you can master it and say, for example, now that even that not small like Facebook, Google, those are also working on this open RAN, because if they can develop some application that they can deploy in the radio access network, so they can give better service to their customers, right? So that kind of involvement are there from the Facebook kind of organization. Even a small organization can come up with some of the parts here and come into the telco business. So now many there were only few in the previous let's say 5 years ago, there are only 4 or 5 telco vendors in the world, but now with the open RAN, many new vendors can come and start doing the business. So do this open RAN architecture. Other thing that I need to highlight is the mobile edge computing. So edge computing is where that let's just assume this example that this is a autonomous driving example, that in the autonomous driving, I told you that we need 1 millisecond latency, right? So if your server is in like in Dubai or in Singapore, that you have that more than 1 millisecond in the transport network, right? But if your server right next to your base station, there has to be no delay, right? So that's the concept here. So now we deploy our application next to the base station, right, with the base station. So then we have much more advantage over having the your server or your application at very far away places. There are many applications in this edge computing. So with all this possible, with that especially this open RAN kind of architecture, where we use the cloud systems and software controlled core network, so then we can easily deploy the application layer also in the base station, right? Even the core network and the application can everything in the base station. So there are certain applications, for example, like you can have the content scaling for the when you're watching a video, that resolution handling and those things can be handled by the edge server in the base station. And you can have private networks. So let's say you are local, you can have your own network just within your base station. So your data will not even go to the operators data centers, right? So because you can handle everything within your premises. Likewise, private networking is there. You can do some offloading, so some computational functions you can offload to the this cryptography, that GPS kind of computational power offload to the edge. This const coding on your voice call, video calls, which can be offload to the cloud edge computer, and the augmentation. So there are a lot of applications. This edge content delivery, so that your content can be stored at the edge. So your video or whatever information, your content delivery network, now you can place at the edge of the network. So there are many applications in this edge computing as well. So this is also some upcoming feature in the 5G and the future network deployments. This I included that I thought you will be interested. So this is completely new thing, that the Starlink. So the Starlink is from this guy that there's a SpaceX project. So from Elon Musk. So that he has started this Starlink, and I think he has done thousands of satellites. They have 1,107,000 satellites already in this space around us. So what he's trying to do, is provide internet to the globe. That means, so the mobile network, so you can have access to certain locations. So when you go some rural area or forest area, so you will not have mobile signal, because that there's no profit margin to operator to have a base station in some remote area, because there is a very low population in that particular area, right? So but what Starlink is, so he created the set of satellites that covers entire globe, entire world, right? So this is what he is doing. So so his beta service is now already started, so in the 12 countries. So it is the largest satellite constellation with more than 1,700 satellites. So 60 satellites they launch at a time. So what is the best thing that we have to identify is that currently the system is not a competition for the mobile operator. So he targets for the people who do not have the access to internet. But the future will be different, because the service is only $99 that you have unlimited internet. So that I mean that previously it was around 20,000, that now more than 30,000. Yeah, but the problem is that here that satellite are not geostationary. So if you tune into a dialogue TV kind of service, you set up your satellite antenna in a certain location, and that won't change. The satellite will be there forever,
They
right?
are
So
working in the
these,
low orbits, no?
yes, those are geostationary, but these satellites that in the Starlink is on low orbit, that is close to Earth, and there is a relative motion with us. So that whatever the antenna that we are setting up with the Starlink is, that has to also be rotated, so that the antenna will track the satellite, and once that satellite goes away, another satellite will come and that antenna will join that. So sometimes there can be the scenarios that you don't have any satellites, so there can be some problems still, because I think they are sending even more satellites, that then after there won't be such problems. Other thing is that
this is similar to handover, no, on the base stations.
yes. So here in the base station actually use a handover, but here the user is stationary, but the base station is moving. That's the difference here.
Yeah.
The other thing here is that they are even this is not still launched in Sri Lanka, but there are some regulatory aspect as well, right? So because if that is Sri Lanka, someone accessing internet, so that regulatory, they want to see what applications and who's using the internet, so those information is required for the regulations. But if you directly access some other country's internet, then can be a regulatory problem. The other thing here is that in the initial launch of the Starlink, they cannot give the service from their own. for that, they need a ground station. For each 300 kilometers, they need a ground station. For if they provide service in Sri Lanka, they need a ground station in Sri Lanka. So you connect to the satellite, and satellite will send that same information to the ground station in Sri Lanka. So then after, there's some way of regularizing this data stream. But now they have already have mesh networks. That means they can connect one satellite to another satellite. Likewise, they can send their data to some other countries and land in some other countries. You may, in this method, so if you browse internet, but it will land in Dubai or Singapore, some other country. So that is a problem in the regulatory wise. So these are some problems that he has to overcome.
The regulator will look after the customer as well as the operator. No? The operator has already made big investments, so it is the responsibility of the regulator to make sure that they will get the return and they will sustain.
Yes, exactly. So they may, but the advantage, even the operator, is that this could be a good thing to connect some rural areas. There are some still advantage because the operator cannot access all the places.
So therefore, it should be properly regulated.
Yes, exactly. So there's another one that compete with this thing that's not popular. That's OneWeb. OneWeb is similar to this. They have already sent satellite. That is a German company. So that also, the two companies, Starlink and the OneWeb, all doing the same thing. So two companies doing this thing at the moment. What I need to highlight here is other things. When you move into 6G, so we have to increase the frequency. That means we have to go beyond what we are using now. So we have to increase the bandwidth
in the spectrum, no?
Yes. Spectrum, yes. But the problem is, if we increase the frequency spectrum, let's say another 100 gigahertz or something, so we can never use in the terrestrial environment because that will not go that much distance. But the solution is a satellite, right? So when you place that base station top of your head or top of your building, so there won't be much constraint or anything in between your satellite and your house, whatever your house antenna. There won't be any barrier. So even very high frequencies, the satellite will work. So let's say in 6G, sometimes we will have the satellite kind of communication, but we never know. Let's see what in the future. So in the 6G, still the discussion is going on. So how the 6G is going on. So in the 3G that we know, sorry, for 5G that we know, mobile broadband, machine type communication, and ultra reliable low latency communication are the three pillars of the 5G. So in 6G, so there can be news that AI, artificial intelligence, to be integrated, and the sensing network. So sensing is a very new concept that comes up with the 5G. So 6G. So these are still in the discussion, but we never know how will be there. So the first sign of the 6G is that the IT user, who is the governing body of this telecommunication in the world, so International Telecommunication Union. So they have formed this focus group network 2020. So network 2030 is their project for the 6G, and so they have created this focus group. So they will define how the 6G will look like. So what are the applications? So currently the one applications is having this holographic type of communication. So this is a new thing actually. So if you have followed the Facebook, so they have recently changed their name to Meta. So that means they are saying they are developing a metaverse. So that completely virtual world. So you are not just watching their Facebook or something in the screen, but you are actually living there. So that's what the metaverse is doing. So this kind of applications, you need very high data rate, because you just not social networking, but you just live with your virtual image, virtual world. So this is how the metaverse, so if you are interested, you can see the videos on this Facebook, what they are doing. So even the metaverse, the later that can be also go to the holographic type of communication. So you may contact someone in the holographic type of communication. So these are in the future. So these need beyond 5G and capabilities beyond 5G. So these applications are the new application that is suggested for 6G development. And so this is the proposed timeline for the 6G. So still we are in the 2022. So we don't know what 6G look like. So the people uh, people come up with different ideas. So these are the how the 6G look like and those things. In 2024 to 2025, we will be having the exactly requirement for the 6G by the ITU. There's this World Radio Conference 23 at there. So we'll have this. So then we can say exactly this 6G network will be look like this from 2024 to 2025, those period. And then there are some 6 years to develop, and 2030 we have to finalize how the 6G network look like. So that's the timeline for 6G. Yes, that is from my side. If you have any questions, please.
Okay, thank you, Chamika. It's very informative and very clear presentation you have done. It's a very good eye-opening to all students. And so this is opportunity to all of the students to ask any question you have. If you really listening to him, maybe you have a lot of questions, especially the software development people. You can see you have a lot of opportunities in future. So it's open for asking the questions now. You can ask by voice or you can type your question.